Okay, guys, so now I'm going to talk about something called osmosis, which is, I guess there's a way you could consider, there's something here that's actually going to be considered a fourth colligative property, but it required a little more explanation than the other three colligative properties. So we've separated it out, and we're going to talk about it a little bit separately. You've probably heard of the term osmosis, and you may be thinking of this specifically as like absorbing something, and that's partially right. The way osmosis specifically has to do with passing solvent or passing solvent through a membrane. So in other words, we're separating, so we're passing solvent through a semi-permeable membrane. So what we mean by semi-permeable membrane is a membrane that allows some molecules to pass, but not others. So in the case of osmosis, so think of a semi-permeable membrane as like a sieve where it allows small things to pass through, but not bigger things. Now, when we talk about osmosis, we're going to talk about a semi-permeable membrane that allows solvent, but not solute to pass. We'll talk about other types of semi-permeable membranes in a little bit, but right now we're going to consider that the semi-permeable membrane, it allows solvent, but solutes are blocked. They can't get through, okay? So, what I'm going to do is I'm going to, well, for one, I'm going to come back to this image in a moment. So, let's talk about osmosis. So let's talk about two solutions of different concentrations with a semi-permeable membrane. So let's say, here's my semi-permeable membrane, and I have like a tank basically, and I've got two different solutions. Let's say one is just pure water, right? And let's say one is, I don't know, like 1 molar NaCl aqueous. Let me write that better. 1 molar aqueous NaCl. Okay. Now, the only thing allowed to pass through the semi-permeable membrane, and let me put some, like, kind of indicate by putting some solvent particles here. So the only thing allowed to pass through the semi-permeable membrane is the solvent. Now, we're going to come back. This is going to be another one of those equilibrium type things where we have two things happening at the same time. So solvent is going to pass through in both directions, right? Solvent can pass through in both directions. And what the whole idea of osmosis is simply this. One of these directions is going to be greater than the other direction. So let's zoom in a little bit and look at the semi-permeable membrane up close. Let's kind of get a real close look at it. And again, we'll keep pure water on the left side, and we'll keep 1 molar sodium chloride, aqueous sodium chloride, on the right side. So here's my membrane. And so now I've got solvent particles, solvent particles, solvent particles, and they're moving through, right? Solvent particles moving through. But I've also got these solute particles that are blocking. So here's the idea. Maybe there's a, well, let me try drawing this a slightly different way. Let me just draw this as, imagine that we've got solvent everywhere, but I've got solute particles in black here. So we've got solute, solute, solute. The idea is on this side, some of the solute particles are going to, because water's flowing both ways, or the solvent is flowing both ways. In this case, it's water. The solute particles are going to be sort of butted up against the membrane, but they can't pass through. They're just sort of blocking. Now, that means that solvent can still pass through, but the solute getting in the way actually blocks some of the solvent. But it's important to understand that what will happen is, you know, the solvent here can go around, or it can push it out of the way, right? Because the solvent going this way can't push it through the membrane, but solvent going this way can push it back, push the solute particle back away from the membrane and get through. The analogy I like to use is from growing up in Kansas. We had a lot of cottonwood trees. And what happened was we'd get a lot of cotton blowing in, and it would stick on the screen door. And the wind would be coming in and push it against the screen door. But of course, the cotton can't get through, and this blocks airflow. As a kid, I would do this kind of weird thing where I'd walk up and I would stand inside the house, and I would blow on the screen and blow the cotton back off of the screen, right? So in the same way, you can't do anything with wind going this way on the outside of the screen, but you can push the cotton back out, going the other way. So the idea being the solute impedes the flow of solvent from that side. So the 1 molar aqueous NaCl, the solute, impedes the flow of solvent from the 1 molar to the pure water. So the net aggregate, I'm going to go back to my macroscopic view, my larger view here, where we have a big view of the, there we go. We have a big view of it. So I've got my membrane, right? And then I've got here, and then I've got solute particles. So yes, there is solvent still going to be able to flow this way and this way. But because the flow from right to left is impeded, there's more of a flow from left to right. Right? So there's more of a flow. So what's going to happen over time is that the difference in the liquid level is going to change. There's going to be a difference in the liquid level. Additionally, something is going to happen to the concentration. One way you can think about this, kind of to help you remember what's going to happen, the system is basically trying to equalize out the concentrations. So the concentration, as this volume is going up over here, what's happening to the concentration of the aqueous sodium chloride? It's going down. Right. So the concentration on that side is going down. All right. Let's try a slightly different, let's try something very slightly different. Okay, I'm going to pause it and erase. Okay. So let's try, I've got my tank, and I've got my semi-permeable membrane that allows solvent. Oops. And what I want on this side is I'm going to allow, so I'm going to have, let's do 1 molar sodium chloride and 3 molar sodium chloride. Okay, so, right? So, remember, the greater the concentration, the more the solvent flow is impeded from that direction. So, you're going to have solvent flow from both directions, and they're both being impeded, but the direction this way is impeded more. So the net direction is this way. The net direction is from left to right, from more concentrated to less concentrated. So what happens over time is you have the solvent changing like this. Okay, so remember, molarity equals moles per volume. It's important to note, solute isn't allowed to pass through here. So all of the solute that was over here is still over here. All of the solute that was over here is still here. It's just that the volumes are changing. So what is happening to the concentration on the left-hand side is the volume is going down, right? It's becoming more concentrated, right? Because the volume's going down. If volume goes down, molarity goes up. On the right-hand side, the volume is going up, which means it's becoming more diluted. In other words, this is trying to equalize the concentrations. It's trying to bring the higher concentration down and the lower concentration up. So it's trying to equalize them out. And that's basically the pressure of osmosis. Osmosis is always going to move solvent from the lower, it's going to move solvent from the side with the lower concentration to the side with the higher concentration. You can think of it as trying to dilute out that higher concentration. So, there we go. So solvent's happening in both directions. Solute molecules literally get in the way. And so, solution with a higher concentration has solvent flow diminished to a greater degree. net flow is always from dilute solution to concentrated. So here's maybe a better drawing. So if you have pure solvent, right, you can see there's 1, 2, 3 going this way and only 2 going this way because they're being blocked. See this one? Oh, so and 4, right? Because this one, it's pushing it out of the way, right? But this can't push it out of the way. If you have 2 solutions, right, this one is clearly more concentrated. This one is less concentrated. You still, if you watch the solvent molecules, 1, 2, 3, 4, 1, 2, right? This one is being blocked, but still we have a net flow as solvent from the less concentrated to the more concentrated. Again, diluting that concentrated solution and concentrating the more dilute one. Okay. Net transfer of solvent molecules continues until one of the following 2 conditions is met. 1, the concentrations equalize, right? So they both, the lower concentration one increases and the higher concentration one decreases until they both have the same concentration, because then the flow of solvent in both directions is exactly equal and there's no net change. Or the hydrostatic pressure on the concentrated side becomes sufficient to counterbalance the tendency. Let me explain what that means. Let me go. This is where I need this image. Notice how, so here we have very concentrated, very dilute. Solvent is going to move from the diluted to the concentrated. Now here, at equilibrium, more concentrated, more dilute. But also look what's happened. We've put more volume in here, and so that the height of the water has increased. Now remember when we were talking about the barometer, this constitutes a certain amount of weight of liquid, a weight of solution, and that's putting pressure. So there's pressure, there's a certain amount of pressure from air and liquid here, but there's more pressure this way, right? So what can happen is there's a certain amount of pressure differential because of the height of the water column, or the solution column. There's a certain differential that will, even if they weren't equal concentrations, would stop the flow, the net flow. In other words, let me try to put this in another way. So put another way, imagine I have two solutions. Again, we're going to do this. This one is 1 molar NaCl. This one's 3 molar NaCl. Now, the net flow of solvent is going to be this way. But imagine I took a big paddle and I pushed down on it. Pushing down on this is going to cause the water to want to escape. And that means it's going to increase the flow of water out of this side over here. There is a certain amount of pressure that I can put on the solution, the more concentrated solution, that actually exactly counterbalances the net flow and it equalizes it back out so that there is no net flow of solvent. Right? The necessary pressure is what we call the osmotic pressure. So, let me erase this real quick. So, the osmotic pressure is the pressure that must be applied to the concentrated side to prevent the flow of solvent. Okay, one thing I'm going to say again, this is related to the colligative properties because it's not the identity of the solute particles that matters at all. It's only how many there are. They're just physically getting in the way. This is the commonality of all of the colligative properties. The particles just get in the way. Okay, so a solution, so this pressure, this osmotic pressure, is basically describing how much the flow of water wants to go from dilute to concentrated. And it's based on the difference between the two sides. The greater the concentration differential, the greater the osmotic pressure. So a solution with a high osmotic pressure will take up more water than a solution of lower osmotic pressure. So and here's a better thing. No net flow, even though this is more concentrated, I'm putting exactly the osmotic pressure to stop the flow. Okay, so So this is important biologically because cell membranes in plants and animals are semi-permeable. We see osmotic type phenomenon. Why am I using the phrase osmotic type phenomenon? Because the term osmosis, specifically osmosis, refers only to a semi-permeable membrane that only allows solvent to move across. Plants and animal cells allow other things, so we call it an osmotic type phenomenon, not osmosis itself. Osmosis itself is only solvent. Some plants can die if they're watered with salt water. Let's talk about why. So inside a cell, right? Inside a cell, you have, inside a cell, and I'm going to put a cell in a little beaker here. Inside the cell, you have a certain concentration. I'm going to call it C cell. Right? Outside, you have concentration C solution, C solution. If we have a really concentrated saltwater solution, right? If C solution is greater than C cell, what happens? Which way does the solvent flow? Solvent always goes towards the more concentrated. If C solvent is more concentrated, is higher, then solvent flows out. This actually dehydrates the plant. This is why, so salt solution outside the root is more concentrated, water flows out, and plant becomes dehydrated and dies. This is why you can't drink salt water. Salt water dehydrates you because of this process of osmosis. It's too concentrated. It actually sucks the water out of your cells. This is also why drinking pure water, too much of it, can be harmful. Your kidneys are designed to kind of equalize this out, but you can overwhelm them. If you had, imagine what would happen if you had the same situation. Let me go back here. You had exactly the same situation, but the concentrations were reversed. So if C cell is greater than C solvent, or C solution, then water flows in. You get too much solvent flowing in, what happens to the cell? It blows up. This can also be dangerous. So you have to have, this is why things with electrolytes are helpful, are important. Electrolytes are just salts, just solutes. Okay, let's talk about osmolarity. I have actually already kind of hit on the concept of osmolarity. This isn't going to be new. What this fundamentally is this. Let's take a look at this. I think you guys will be able to get this from what we talked about the other colligative properties. If I have 1 molar sodium chloride, actually, if I have 1 molar sodium chloride and 1 molar magnesium chloride, which way does the solvent flow? And if you get this, then you already understand osmolarity, and there's just a term that goes with it. The solvent is actually going to flow in a net direction this way. Why? I mean, they're both 1 molar, right? So it shouldn't flow. You might think it wouldn't flow any direction. But what's happening is, remember, osmosis, like the other colligative properties, is based only on the number of particles in the solution. Magnesium chloride dissociates into 1 magnesium ion and 2 chloride ions for a total of 3 ions. Sodium chloride dissociates into 1 sodium ion and 1 chloride ion for a total of 2 ions. So this one has an effective concentration of 3 molar stuff, ions. This one is only 2 molar. Right? Because it doesn't matter what the things are, it just matters how many moving bits there are. And this one has more moving bits than this one. So to find the effective concentration to apply to molarity, we already did this. You just multiply the concentration times the number of ions that it produces. And this is what's called osmolarity. Osmolarity is this newly calculated number. Actually, wait, hold on. Yeah, osmolarity is that effective concentration. So it's the molarity times I. I is just the number of individual particles produced from the dissociation of a formula unit of the solute. So a solution of 2 molar glucose, glucose is a molecular compound, it doesn't dissociate, has an osmolarity of 2. Magnesium chloride has an osmolarity of 6, because it dissociates into 2 chlorides and a magnesium, 3 ions, times 2 is 6. So it's osmolarity that indicates the osmotic pressure. And frankly, it's osmolarity that also you can use to figure out what's going to have the greater boiling point increase, freezing point decrease, and vapor pressure decrease. Osmolarity is just the name for this concept that I'd already introduced. So it's the effective concentration, meaning dealing with actually how many particles there are. So the osmotic pressure of 2 molar magnesium chloride has an osmotic pressure 3 times that of 2 molar glucose because it produces 3 particles, where glucose only has 1. Okay, a couple quick terms to go with something I already introduced. Imagine, so going back to that idea of the cell, and you have the concentration of the cell, the concentration of the solution. So we have 3 terms to describe the solution. A hypotonic solution is something that has a lower osmotic pressure than that within cells, right? So in other words, its osmolarity is lower, right? Hypo meaning low, it's lower. So that's the situation where if I put a hypotonic solution, C solution, C cell is greater than C solution because the solution is hypotonic. So this is where water flows to the more concentrated and it blows up, right? So red blood cells placed in a hypotonic solution take on the water because they're more concentrated. The solution, hypotonic, is less concentrated. They take on water, swell up, and explode. This is called hemolysis. Heme meaning blood, lysis meaning cut. So basically destroying blood cells. Hypertonic, what does hyper mean? Hyper is greater, is above, higher than. So this is a solution with a higher osmotic pressure than within cells. And what happens then is the blood cells lose water to the solution, and they shrivel in something called crenation. So take a guess as to what you think a solution that has an equal osmotic pressure to cells would be. The answer is isotonic. Iso meaning same. This is equal. This is healthy. So here, they're in hypotonic solution. They're sort of, they're about to blow up. This is crenation in concentrated sodium chloride, right? It's hypertonic, so it's losing water. This one's taking on it, swollen up, you see. And this is neither swell nor shrink in an isotonic solution. And that's really all I have to say about osmosis. I'm quickly going to talk about the idea of dialysis, because you'll probably see this. It's an osmotic type process that allows small ions and stuff, small things to move through the semipermeable membrane, but not big things like proteins. This is specific for isolating proteins. So, in dialysis, instead of solvent moving into the bag, which will happen, ions will also move out. So you actually get ions out here too. But now, if I want to separate out ions, these impurities, from, say, a protein, what I can do is I can flow water through, and it's going to keep, as the ions come out, they're going to come out, and it's going to keep moving them along, moving them through. Eventually, all the ions will leave, and then the proteins will be trapped in there by themselves. And that's really all it is. That's all dialysis really is, all we're going to talk about dialysis.